In this video recording, we're going to be looking at equilibrium lesson number 4, which is all about manipulating equations. Now, when we say the word manipulating equations, okay, this is going to refer to a few different things that we can do to change an equation and how that's going to affect the way that we calculate the equilibrium constant KEQ. So there's three different ways we're going to manipulate our equation. The first one is going to be changing the direction. So a change in direction, okay, is going to change the KEQ to be the reciprocal of that. So if we look at this example, PCl3 plus chlorine gas makes PCl5. There's our reaction written in the forward direction. We still write KEQ as always our products over our reactants. So here we've got our product on the top and our reactants on the bottom. If we were to give this a value, so let's say KEQ was equal to 5, we can see how that number will change when we flip the reaction. So if we look at the reverse, we now have our PCl5 is now written in as the reactant, okay, and the PCl3 and Cl2 are written in as products. So when we look at how the KEQ expression changes, we're seeing a flip from top to bottom, okay, because now our chlorine gas and our PCl3 are products, so they're going to be on the top, okay, and the PCl5 is going to be on the bottom. So if we look at the number value for a KEQ expression like this, before we had 5, and any number that's just written as is, you can think about it as being over 1. So if we take the reciprocal, just like we did with just the expression, the way we wrote it out, that would then give us 1 over 5 as the new KEQ value for when we change the reciprocal of the reaction. Okay, so overall, we're seeing that this KEQ, when we flip, when we reverse, we're going to get 1 over the KEQ if we change it in that way. The second thing we can do to change a reaction that will, again, affect what the KEQ value for that reaction is by multiplying, okay, the coefficients by some number. So you can multiply it by 2, you can multiply it by 5, you can multiply it by 1/2, a variety of different things that you can do, but basically they all work the same way anytime you're multiplying your coefficients by some number. So again, let's look at the same reaction. So we're starting off with, this is our original reaction here, and we're going to change that reaction to get to here. We're multiplying it by 2. So see how we're going from a 1 coefficient there to a 2 here. Again, 1 and 2, and then 1 and 2. So if we multiply our original reaction by 2, we now get this new reaction. And to solve for the KEQ of that reaction, okay, anytime you have a coefficient in a balanced reaction equation, it then becomes an exponent when you're writing out your KEQ expression. So that means that the KEQ for this reaction would then become, if we look at the number version, it would be 5 squared. So we're not multiplying the 5 by 2, we're squaring it. Okay, so we're taking that original KEQ, we're squaring it to get the new KEQ for the new reaction. The third thing that we can do when we're manipulating equations is we can actually add multiple equations together to get some kind of target equation. Some reactions are very difficult to observe or very difficult to measure things in an actual physical setting. So what we can do is we can take 2 or more reactions that are easier to perform in a lab setting or easier to measure something about, and we can do those reactions and then measure the KQ values for those and then add them together to get our target equation that might be more challenging to actually do in like a laboratory. So our example here for this one, okay, is we've got two reactions here that add up together, okay, is going to give us, this one is our target reaction. So adding equations together, we're going to multiply the K values. Okay, so anytime we add equations, we're going to multiply the K values. So let's walk through it. For this reaction, the first one, we've got 2N2 plus O2. Okay, so those species we're seeing in our target, so that's good. But the last one, this N2O, is not part of our target equation. So we're actually going to want to see how that is going to kind of like disappear. In our second reaction, there it is again, that N2O. And then we've got oxygen, which again is in our target equation, and our nitrogen dioxide, which is in our target equation. So the one thing that we actually don't want, okay, is this 2-dinitrogen monoxide. But because they're on opposite sides of the arrow, what this is telling us is that in the first reaction, that's being made, but in the second reaction, it's being consumed. So it's gonna cancel out, and it's an equal number, so 2 and 2. So they're gonna cancel out on both sides of the arrows, get made, and then get used up in the same proportion. And then when we bring down, we add our two reactions together, you can think of that as a 1 plus 3 is gonna give us the 4 oxygens there. Okay, and then that brings down our nitrogen dioxide. So we can see how when we add these two reactions together, we're going to get our target reaction. Now, what does that mean for our K values? Now, let's again take an example of using real numbers. So we're still doing products over reactants. Let's say the KEQ for this reaction, we're going to pretend that it comes out to being 2. I'm using simple numbers just to help people see the way in which it works, but you'll still often get K values that are either bigger or like very small, as we've seen throughout the course so far. For the second reaction, we'll say that the KEQ value is 7. So we'll do a little practice with some real numbers. Okay, this KQ, okay, is represented here. Okay, if we're looking for the K of our target reaction. And then the second reaction is this one. So there's that one. So when we multiply them together, okay, we're going to see that this N2O that we canceled out in our reactions, we're also going to see that cancel out N2O and N2O on the top and the bottoms of our fractions. So again, they're going to get canceled out here. Okay, and then when we multiply them together, we're going to see that it's going to create our target KEQ from that target equation. So my nitrogen is there and there. Okay, my oxygen, there's there and there. So that adds up to that one. And my nitrogen dioxide there and there. So that gives us our target, which is how we can sort of prove that when you add reactions, okay, you're going to multiply the K values. So if we were to do this with our numbers, KEQ would be equal to 2 times 7. So the KEQ for our target reaction would then be 14, and that's how we would get our final answer. We'll do a couple of practice questions. So firstly, Here we have a reaction, okay, with the KQ value of 115. So we're going to see how are we manipulating that equation to get each of the following equations down here. So for A, to get from our target to this A reaction, you'll see the coefficient is changing. It's still in the same order, but we're multiplying it by a half. So we did times a half, or you can say divided by 2. Okay, which means that the KEQ I'm using the little like asterisk, the little one, to show that that's for this new reaction. Okay, is going to be equal to the KEQ of the original, but it's going to be square rooted, or you can think about it as KEQ, okay, to the power of a half. So remember, when you multiply by a coefficient, okay, that coefficient, okay, is going to become an exponent. So now we can put that number in. So square root of 115 is going to be the KQ for this reaction, which is going to come out to 10.7. For reaction number 2, or B, I guess, here, okay, we'll notice again that 2 becomes a 1, the 1s become a half. So again, we're multiplying by a half, but we're also reversing it. So we're flipping the products and reactants. So the KQ for this reaction is going to be equal to 1 over KQ to the power of a half, or you can write it out as 1 over the square root of the original KQ. So square root is the same thing as to the power of a half. So when we reverse it, we're getting the 1 over, so we're taking the reciprocal, as well as multiplying by a half gives that square root. So then the KEQ for this reaction, okay, is going to be 1 over the square root of 115, which is going to give me 0.0933. So I'm keeping 3 significant figures sort of throughout because I started with 3 in my original KQ value. Now this is getting a little bit messy, so I'm going to erase some of this just to make room for doing the last one. There we go. Makes it a little bit easier to see. So here's our original equation still. And from here down to equation C, how are we manipulating that original equation? Here, we're going from a 2 to a 3. So we're multiplying it by 1.5. And we're also flipping it. So again, we're reversing. Okay, so we're going to take the reciprocal again. So KEQ for this reaction, so KQ prime, we can call it, is going to be equal to 1 over the original KQ to the power of 1.5. So 1 over 115 to the power of 1.5 is going to be equal to sorry, I don't have this one actually calculated, so I'm just quickly typing it into my calculator. To the power of 1.5 is going to give me 8.11 times 10 to the negative 4. Remember, KQ does not have any units. So it doesn't need anything else written there. Okay, let's do one more practice question, this time with one of those adding up equations type practice. So moving on to our second practice question. Given the information about equilibrium constants below, find the value of the equilibrium constant for the third equation. So we've got two equations to manipulate and then add together to try to get our target equation, where the k value we can figure out by multiplying the k values of the two that we're manipulating. So in this case, the easiest way to go about trying to figure out how you need to manipulate those first two equations to be able to add them up and get the third one is to look at your target equation, which is this one, and try to figure out each piece at a time. So I'm going to start with this NO. When I look at the two equations I'm using to add up to my target, the only place where I see NO again is in this one. So here, this is on the wrong side of the arrows. It needs to be flipped onto the reactant side. It also needs to be divided by 2 because we don't want 2, we only want 1. So we're going to change this reaction. We're going to multiply it by 1/2 and reverse it. And I'm just going to rewrite it out because it's a little bit easier to see that way. That's going to give us NO is going to be 1/2 N2 plus 1/2 O2. And the K for this one, now that we've manipulated it, is going to become 1 over the square root of that number. So anytime you manipulate an equation, you also need to manipulate the K value. Next, I'm going to look at the oxygen. So again, I'm referring to the species in my target equation, figuring out where am I going to get that. So 1/2 O2, I already have 1/2 O2 here. So I want to make sure that that kind of stays there. There's O2 in both of the reactions that I'm manipulating. When that happens and it's in more than one place, I recommend that you leave that species to last because it's a little bit harder to see what you maybe need to do. So I'm going to skip that and I'm going to move on to looking at this NO2. Now, NO2 only appears in this first reaction, and it's already in the right place and in the right amount. So I don't want to change that equation at all. I want to leave it as it is. So I'm going to take this equation and I'm going to rewrite it out. Okay, so this one, I'm going to rewrite here, no change. I don't want to change it. So that's going to give me 1/2 N2 plus O2 to give me NO2 there. And that K value stays the same. So now I'm going to look and make sure that when I add these two equations up, that they will actually give me my target before I solve for the KQ of my target equation. So NO is going to come down. Okay, there's nothing for it to cancel out with or add with, so it's just going to be NO. Then still on this side of the equilibrium arrows, I've got some N1/2 of an N2. But I've got that on both sides of my equation. So 1/2 and 1/2, opposite sides of equilibrium arrows. So it gets created and then it gets used up. So it's going to kind of cancel out and it's not going to appear in my final equation, which is good. That's what I want. For my oxygens, okay, I'm now going to be able to see better how I'm going to add them up. I've got 1 oxygen on this side, which you can think of as like 2/2, seen as this oxygen is 1/2. And when I add them together, when they're on opposite sides of the equilibrium arrows, you're kind of like subtracting one from the other. So I'm starting off with a whole oxygen here, and I have to subtract 1/2 an oxygen from that side, which is going to give me an overall of 1/2 O2 that's left over on the reactant side of the equilibrium arrows. And finally, I've got my NO2 at the end. So now It matches my target. I've double checked that everything kind of crosses out and cancels out correctly. So my KEQ for the target reaction, okay, is going to be the first one times the second one. So 1 times 10 to the power of 45 times 1 over the square root of 1 times 10 to the power of 60. Okay, and that's going to give me 1 times 10 to the power of 15 as the final KEQ for my target reaction. All right, we'll do some more practice of this in class, and if you have any questions, we can take them up in class, or I'll see you at Grove Time.